Here at the conclusion of our presentation of basic probability distributions that are commonly used in engineering, a file that you will want to have access to is the table KP6-1. It has a summary of some of these common probability distributions, particularly as we can compare them from discrete time to continuous time, or space is another way to look at that. Right? And these are just happen to be some of the most commonly used ones out there. They certainly are not all of the commonly used ones, but they're organized here because of the relationship between the discrete space and the continuous space. For instance, if we're interested in how many successes or arrivals there are in a fixed time interval, that's how many, not the time until the first, but how many in a fixed time interval. When time is discrete, then we get this binomial distribution. The binomial distribution has this nice binomial coefficient. That's the n factorial over y factorial, n minus y factorial. And here's our then probabilities with constant success, and then the 1 minus that probability there. So that's a very specific sequence in terms of the numbers of successes and failures that are happening, and then the binomial gives you then all the permutations that have the same kind of number. Right? There's your expected value, there's your variance that goes along with that particular number of trials. Right? When you go and say we got continuous time, then we get into the Poisson process. Again, this is how many successors or arrivals are in a fixed time interval. Right? Now, here, one of the things that you have to keep track of are the symbols. This is a symbol nu as opposed to the parameter lambda, and here's one definition of that. That's reverse of what you see in Montgomery and Runger, but it's very common out there as well. And so what you really have to focus in on is the meaning of the definitions as opposed to the specific symbol. And I know it's confusing, but just keep track of that. Note that if you want to, you can grab the PDF file and you can change it, overwrite that, do any symbol that you want there if you like. If we're interested in how long until the first success, that's the geometric distribution, and the geometric distribution is in itself a very special case of the negative binomial, right, which is down below. Negative binomial is just generally speaking how long until the kth success. So if you let k become 1, that's how you get the simplified version here, and you get the geometric distribution. Note the memoryless property that is sitting there, and then when you go into the continuous time domain, you get the exponential model. And the exponential model in itself is likewise a special case of the gamma distribution down here, which is more generally for k, how long until the kth success. Right, so here again we get the side-by-side nature of discrete time versus continuous time, or discrete space versus continuous space. We can reinterpret what the meaning is of these random variables. You get a little, again, a definition down here of some of these symbols, and you just have to keep track, again, of what symbols are being used. It's not universal. You would certainly wish that it were, but it's not, and it can be confusing if you're fixating on the symbol and not focusing on the representation. And so this table can be very handy as you're going about doing problems from a practice standpoint, also just from the standpoint of doing some of your homework exercises, and then later on when we get into exam type situation, this is helpful. Of course, there are other distributions that are out there that we've talked about that are not listed here. The uniform discrete versus the uniform and the continuous one, two very simple models. You've got also the normal distribution over on the continuous side. You've got the log normal on the continuous side, the Weibull, the chi-squared, the Erlang. All those are oftentimes used in engineering applications, manufacturing type applications, and we will see particularly the normal distribution and a special case of the gamma called the chi-squared distribution will come back to us later when we do hypothesis testing and that sort of thing. And you could certainly, if you wanted to, build a similar table as what you have here. I had suggested to you that you first saw this in one of the earlier lessons, KP2, that you might have the definition over here on the left-hand side and put over here on the right-hand side some of the typical common assumptions and applications that you might see those, and I encourage you to consider doing that. Again, sort of keeping your table, keeping track of as a reference of how you might want to use this later on.